In the second part of Module 4 about e-motor concepts, we will go into more technical detail. Still, we will have a further material just for teachers in the physics area that goes into very high level of detail into physical laws, principles, and formulas, which is an additional module. And this additional module we recommend the physics teachers to read in addition to this lecture. You find that material online. These are the subjects which we will describe in this lecture with a little bit more technical detail than the introductory part was. A system engineering view from viewpoint of techniques and physics, a software development IT view, why mathematics is involved, interesting topics for biology, interesting topics for chemistry, and interesting topics for ethics. And for each of them, we will list some details we recommend teachers to deal with and teach students in their subjects. Let us start with the system engineering view and the technical system picture. This will include an overview of the sensors we are using in an e-motor concept, the concept of an inverter board and the circuit board, three-phase electric motor concepts, measuring torque, speed and angle speed or rotor angle, and additional safety issues which are to be dealt with in modern cars nowadays. This slide tries to explain the e-motor concept as a system overview. What you can see from left to right is that first comes from a vehicle bus. That's usually a CAN protocol or in Volkswagen a FlexRay protocol and so forth. So by communication protocol we get over the vehicle bus a demanded torque, a torque direction and speed. And what you then see is a vehicle controller, which is an electronic control unit which runs usually at around the 12 volt power and has a software on it which is called FOC, Field Oriented Controller. And this ECU is having the algorithmic intelligence developed by software so that it reads the demanded torque and speed. It reads the current speed and rotation of the motor. It reads also the rotor angle position from the resolver, which is actually here the sensors, and calculates how to actuate T1, T2 and T3. T1 and T2 and T3, these are these huge semiconductor elements which are on the circuit board of the inverter. You see the inverter circuit just in gray in the middle. And this inverter is providing current I1, I2 and I3 to the three coils inside the three-phase motor. If you put electric power on a coil, then you create a magnetic field that can drag the rotor inside the e-motor. And these three currents are going to three differently positioned such coils that are three different magnetic fields that can drag the motor in a circle to create a rotation per minute by the rotor, which is then the rotation of the motor. What is special and why we separate here the electronic control unit from the inverter board is that an electronic control unit is like your computer at home. It can calculate something, it can provide through an interface some information. In this case it actuates by an interface the semiconductor elements on the inverter, but it's not capable of handling huge volt. And in an electric car we have a very strong battery, a 400 volt battery normally when we go for a complete e-motor drive. This could be even bigger when it's a truck, so the 400 volt is normally for a passenger car. And therefore we need a separate circuit which is capable of handling this huge voltage and providing semiconductor switches for 400 volt. And this is why we need the inverter board separate from the electronic control unit. Some elements here used are the ECU, which is an electronic control unit. An ECU contains electronic software and is connected to a vehicle bus where we get the commands from, or we provide even information to the vehicle, like the rotation per minute of the motor. Field-oriented controller, this FOC is a standard term. When you enter that into the Google, then it's a field-oriented controller. It's a special piece of software that's specific for the control of e-motors, usually three-phase e-motors. And ready-to-use software is provided, which you can adapt. Usually the field-oriented controller bases on a sinus shift of 120 degrees, so a mathematical function used in trigonometry because we place these different magnetic fields or coils in a circle with a 120 degree difference. 3 times 120 degrees, 360 degrees, which makes the full circle. Yeah, and then T1, T2, and T3, that's called in the video we have seen in this e-motor concept video, is what they call the MOSFETs. They're also called IGBT switches to switch electric power. And the MOSFETs are, in this case, semiconductor elements to switch high electric power of 400 volt. And when we put the I1, I2, and I3 currents on the 3 coils, we call them the phase currents. These are the 3 phase currents which are actuating the magnetic fields in the motor to drag the rotor. What is not visible here but has to be mentioned is that the rotor itself inside is usually a permanent magnet rotor, which is made out of special material so that we have a very strong permanent magnet inside the motor. This slide shows that when we want to control an e-motor, we have to measure back some of the values how we control the e-motor. For instance, we provide currents I1, I2, and I3 on the 3 legs of the motor. In this case, the leg is the coils we have mentioned before in the previous slide. And we would like to measure back, of course, if these currents are operating correctly. So we would have sensors measuring back the current sensor 1, the current sensor 2, and the current sensor 3. And then there are some mathematical and physical laws with which we can check that the currents are correct. Which means that when we control a motor, there is a Kirchhoff law, for instance, that the sum of the 3 phase currents should be around 0. So we have some mathematics and some diagnostics where we can see if the e-motor is perfectly controlled or not, because if the Kirchhoff law or the 3 phase currents are not 0 and it's not correctly coordinated, the 3 phase currents, then the motor will not run perfectly. So it would not produce the torque expected. This slide shows a more detailed view of the inverter board. So the power supply comes from the 400 volt battery, and we have T1, T2, and T3 as the semiconductor elements to switch the electric power on the 3 coils. But what you see is when we look into the level of detail, we have not only T1, T2, and T3, we have T1 dash and T1 2 dash and T1 3 dash. We call them high and low switches. Why high and low? Because when we connect to the motor, we can connect via the positive or negative electrode. And this way we can switch the pole. And the pole switching is necessary in an AC motor, asynchronous e-motor, And in most of the vehicles, we're using AC three-phase motors. And the FOC, which we have heard before, which is this software component, is the algorithm or contains the algorithm that controls when we switch to high or low switch in a tacted way to control the E-motor. Basically, we always switch between high and low switch, and in the next slide we will explain why that is needed. Here on the slide, on the left side, you see how Wikipedia is explaining the E-motor concept. You can see the three coils, and you see the three phase currents, I1, I2, and I3, and by applying the phase currents on the coils, magnetic fields are created that drag the rotor, and the rotor itself is in the middle, which is a permanent magnet. And we say we have three phases because we have three different currents and we have three different magnetic fields that can drag the rotor. And the slide also shows that we have a 120 angle difference in positioning the coils. Also, the slide explains in Wikipedia how the Kirchhoff law is applied, where the sum of the three phase currents should be around zero within a limit. Also, here as a summary explained is the difference between the high and low switch, like here with T1 and T1 dash. The electric motor is connected between high and low switch, and thus the phase can be connected to either positive or negative electrode of the battery. In this case, the pole changes and the direction of the magnetic field changes. With an AC supply, which is the typical motor we have meanwhile in cars, which is an AC three-phase electric motor, both the magnetic field and rotor current change direction every time the supply current reverses. That means the force on the motor is always pointing the same way. There's an explanation of why this is so, which is provided here by a link. What I'm presenting here by video is also available as a material in PDF, where you can even click the link and find the details. This slide shows two types of rotors. One is a permanent magnet rotor and the other one is the induction rotor. Permanent magnet rotors have magnets integrated into the rotor, which interact with the magnetic windings to create a rotating magnetic field, creating the torque. The other one is the induction rotor used in induction motors, and here to create these magnetic fields the rotors include rotor windings. The field-oriented controller running as a software on the electronic control unit is actuating these MOSFET switches, which are the semiconductor elements to produce the I1, I2 and I3 currents. And there is a mathematical algorithm behind it, which is basically in a 120 angle phase shift, these switches are actuated. We will later in the more physical slides, because we have an extra slide set for teachers in physics, we explain that this shift is done by PWM, which is a special method to actuate the switch only in specific times. And this algorithm, because we base on a sinus function, allows also that we use trigonometric functions as algorithms in the controller software to calculate the angle rotor, or the rotor angle actually, and the angle speed. The E-motor concepts also include a number of sensors so that we are measuring the torque and frequency and rotation per minute. This is called in the slide a resolver, but in reality a resolver can be based on different measurement principles from sensors. Here a simple example is that we can have a mathematical model calculating the speed of the motor where the formula is Nd is equal to Fn divided by P. Nd is the torque per minute. The Fn is the frequency in hertz measured by oscillation, and P is the number of pole pairs in the windings. So for instance, with a pole pair is 1 and frequency measured by oscillation is 50 Hz, the RPM per minute, rotation per minute of the motor would be 3000 RPM using that mathematical formula. These mathematical formulas are implemented in software by the field-oriented controller, which we have seen as a piece of the software running on the electronic control unit. There are different measurement principles so that we can measure the speed or the rotor angle position by sinus and cosinus. So here is one example. Many e-motors use a Hall sensor, which is a magnetic field sensor that measures a tick every time when a rotor winding is entering the field, measured by a peak in the sinus curve, and the number of Halls represent a specific degree. Hall sensors usually provide a bus which delivers sinus and cosinus of the angle as digital values to the electronic control unit, and in the e-motor ECU the sinus and cosinus are used to calculate the angle position of the rotor. Also, Hall sensors operate at a very high speed, usually delivering such a sinus and cosinus value every quarter of a millisecond. When we come to the slides of for the physics teachers, which are also provided in addition to this presentation with a lot more details on how the physical principles are implemented, there we will see another measurement principle where there is a laser sensor used where we can measure by the number of ticks of light effects. Yeah, so if a certain position has been achieved, so that like here a tick by a magnetic field, in the other case would be a tick by a light indicator. Here are two slides about safety issues with which we have to deal with when we are using e-motors in cars. One issue mentioned here is the maximum torque limit. So e-motors are mechanically constructed for a certain RPM, rotation per minute. We can speed up the motor higher than the mechanical maximum, and therefore the controller software on the FOC in addition gets some diagnose software so that we are not requesting a torque which is higher than the maximum torque. This is safety critical because if the motor would break, it would block the motor and later block the wheels, and it comes to uncontrolled deceleration of the vehicle. The other thing is that that you have induced power, induction power, and when you decelerate very much, which means we have a high current, when we have an immediate switch off of the motor during drive, and this current could be big enough so that it destroys other electronic control units in the car. Now imagine that you have this kind of immediate switch off, a high current, and the fuse not working, which should protect it for creating the short circuit for the other ECUs in the car, and it would destroy the steering control unit and also the steering control lock unit, which would mean it would put the steering lock in while you drive, and you cannot steer anymore, even if you drive at, let's say, a medium or high speed. So it's very safety critical, such a situation. Another safety case is that the currents with which you control the e-motor are not properly working, which means we have learned before that we use the Kirchhoff law to check the phase currents and if they are correct. And let's say we would not control that and would not find it out and continue driving, this would lead to a loss of power in the produced by the e-motor. Imagine you are driving on the motorway, and suddenly, and behind you is a truck. Yeah, you drive at 100 kilometers per hour, and suddenly, without having your brake lights on, your car starts to decelerate. Then it could happen that you have a rear accident with the other vehicle. This is the case of wrong torque. Also, with e-motors, we have a different situation when we start up a car. This is the point 4. In the old times, when you start up a car, then you have to switch on the ignition, and then, of course, until the power is transported by the motor, the ignition must work. In this case, in case of an e-motor, it's a button and the battery and immediate power. And when you have immediate power, just imagine you have some electric car, you park it in front of a cafe, and then incorrectly the button has an electric fault and says switch on the engine, and then the car would start to accelerate. And therefore, this is a safety case to really recognize that the driver really has confirmed to switch on and wants to accelerate the vehicle, because it could be a false ignition on. This slide shows us a summary of topics which are addressing different subjects of teachers and are linked to the e-motor concept. In physics, we have the terms current, voltage, electric circuit, semiconductor, magnets, magnetic fields, windings, connection between electric currents and magnetic fields. Thus, you teach the students in school about OSI layer model, which is the basic model for communication, and which is also used for the CAN communication within, or bus communication within vehicles, for instance between the battery management system and the e-motor control unit, or between both and the vehicle. When it comes to IT and software, then we have learned that there is a field-oriented controller programmed on the electronic control unit that is actuating the three-phase currents and uses information about speed and current motor and rotor position and rotation per minute to control the currents towards the motor. Also, we have learned that it includes a lot of diagnose functions to measure the current, the angle speed, the rotor angle using sinus and cosinus. We have their mathematics because we use mathematical functions there of sinus, cosinus, angle speed, phase shift. Also, we learn then later, when we look at in more detail at the software program, that it has a lot of vector arithmetics in it, so that we can express the direction of magnetic fields, for instance, in mathematical terms. We have biology, where there's an impact on biology because we have no CO2 emission. Also, noise goes down. We have ethics and philosophy, where people would have to accept safety issues of e-motors in future. They have to accept that we have 400 volt power lines in the car, so probably you shouldn't open just your car by yourself anymore. And danger of not hearing a car, because an electric car is no noise at low speed. Not talking about what we have talked at the introduction, that actually when we switch to e-motors, we need much less petroleum. When we need much less petroleum, this has an impact on the world market and might lead to further conflicts. And in chemistry, we have learned about materials which we use for permanent magnet motors and rotors, and also the lithium and the setup of 400 volt lithium ion batteries. To see the e-motor alive, we have set up a laboratory using specific inverter board, electronic control unit, and e-motor. This was done in partnership with Professor Miran Rodic from University of Maribor. And he is a partner in the so-called Automotive Quality and Knowledge Alliance project, where TU Graz, FH Ioneum, TU Ostrava from Czech Republic, FH Düsseldorf, Grenoble Institute of Technology of France, and also Slovenia with University of Maribor are partner. And this shows one of the laboratories and also the technology setup, and names the different components which we have mentioned before. Also in module 4 you found at the beginning of the course such a video which shows the laboratory, and also you hear the sound of ELIC and you see the positioning of the pieces of the e-motor system during the setup and the play of the video. When it comes to IT and software, the field-oriented controller software, of course, there are links here where you can find specifications of that software. Also, there are ready-to-use programs which you can adapt or configure to your own purpose. Large industry like Magna, Bosch, they develop their own FOC. Others, like a laboratory inside a university, might buy the software and configure it by parameters to their needs. What does the software do? It controls the three-phase currents. It's ready to use in software development kits, and it's an embedded software. Usually this embedded software is displayed, you get an extra GUI, which stands for Graphical User Interface, which is developed by model-based software where programmers are using MATLAB as a programming design language. Here you also find a link to ready-to-use software if you want to program an FOC controller for an e-motor. There are development kits. This is only one example of these development kits. They are specific to the inverter and controller boards which you are buying, but usually get then, when you buy them, also this development kit, like here the STM32PM FOC software development kit, and you get also the graphical user interface. In most cases, you just configure that software and you can use it, but in more specific cases, like I mentioned, when we adapt it to real products in these customer sites, then these parts of this program are reprogrammed as controllers, which are then used inside the software. Usually the big companies like Magna developed at one time, then they offer it as a library which can be configured to all the other sites inside the company. If you're more interested in setting up your own e-motor, we've provided also a slide set for the laboratory setup, what kind of inverter board or ECU board was used and what kind of motor was used. You find it also here in this area of learning for the e-motor. It's called the laboratory setup slides. And what you find here at this link is then a description of the software used, and this gives you then an opportunity, if you really want to set up your own laboratory and work with it, that you find also the software and can configure it. Here is the link leading to a software which offers key features like features, tree shunt current sensing topology, sensorless operation based on state observer, which is a mathematical model to calculate the RPM, speed and torque control, native support, and so forth, and full customization and real-time communication. So when you get this toolkit, then it offers you all the specifications, descriptions, configuration options, and you can also tailor and adapt the software to your needs. When looking at this software running on the electronic control unit, for instance the FOC, the field-oriented controller, and we look at what algorithmic functions are used when the programmer is programming this system, then here's a list of what mathematical functions are used. And when programmers are using that, then it's good if they have a basic understanding of these mathematical functions. For instance, vector arithmetic. The program uses calculation of normalized space vectors, where students learn in school, I think, normalized space vectors. There is a number of trigonometric functions used in this program: calculation of angle speed, calculation of phase shift, to actuate the switches in 120-degree position. In this case, it's mentioned with the P, 2P, 1/3 of 2P is actually 120 degrees. Modulation of phase waves in form of sinus curves and basic functions. Also, they use a differential equation. This is what normally students in school learn in the 7th or 8th class of gymnasium, or comparable to other schools, probably the same level, where they use differential equation over time to see the differential equation over angle speed, so that we can calculate over the angle, so that we can calculate angle speed, or also integral to calculate the space between the angle vectors, which is also a value or an arithmetic function which we are using within the FOC program. Therefore, this basic understanding of these mathematical functions is needed when you want to understand the field-oriented controller software, or you want to adapt it for your purposes. Mathematics is therefore helping to implement the software, and without mathematics, physical equations could not be calculated. Here again is a link to the description of what mathematical algorithms we are using in an FOC controller concept. E-motor concept is not a topic just for teachers of physics. Also other areas like biology are to be involved. This slide gives the biology teachers 3 central questions they could look at and discuss with their students in school. What do we do with million tons of lithium? Is zero emission reached by e-motors? Or what is necessary to reach it? Is electric power production really clean? What we did here is we provide links to recent articles about these questions, and they could be an input to school and to discussions in the biology class in school. In the previous slides, we have learned that for permanent magnet rotors we need rare earth materials, so very strong magnets. So do you know all rare earth materials that can be used for strong permanent magnets, which we could use in e-motors? Here's a link, for instance. Do you know that lithium batteries can have an H-gas explosion, which is one of the big dangers of a lithium-ion battery, especially at the size of 400 volt? Here's a link with it, and please read and discuss it. Or did you know that e-motors need lightweight vehicles and that polymers are used for vehicle building? Because nowadays everyone believes, hey, a car that's steel, or some kind of prepared steel so that it has the lifetime. But in reality, we are working on new versions of polymers so that we can have lightweight materials in cars which have similar behavior like a steel car, but it's much lighter. And we need this research at the moment, because we have to guarantee that with an e-motor you can drive the same distance like with an combustion engine, and that will only work when we can reduce the weight of a car. Also for psychology and ethics, we put up here some interesting questions. What international conflicts can appear if countries depend on oil, but we would not need the petrol anymore? Or did you already think about the challenges of this generation to handle energy problems? Where does the power for e-cars come from? Or is there a connection between business ethics and the use of electric cars? Also, for these three main topics, we provided links where this is discussed. And we asked the teachers to think about it, discuss it, but maybe also put it on the table in the classrooms so that we prepare the young generation to deal with these questions.